This is the biomechanical analysis of the video that you just saw, which is me performing a thruster. To give you some biometrics, I went ahead and recorded my body mass, which is 88.64 kilograms. Estimated 1/7 of my mass to be each leg, which came out to 12.66 kilograms per leg. I also measured my tibia length, my femur length, and my torso length, since those are the three rigid parts that we're going to be looking at through the movement. Okay. The start position will be the bottom of the front squat for the thruster, which I have the angles recorded here. What I did was used a protractor on the screen and measured each of the angles and then recorded all that data. So starting position, the foot to tibia angle is 55 degrees, the tibia to femur angle is 30 degrees, and the femur to torso angle is 35 degrees. As we move on to position A, this is the first 3/10 of the second in the movement. It starts by moving to 65 degrees at the knee, and I recorded that as a angular displacement of 0.17 radians with a arc length of 7.31 centimeters. And I have all the math recorded here. So this would be 0.17 is the angular displacement divided by the time, which is 3/10 of a second, comes out to 0.57 radians per second. This will be the same math that I used throughout, so this is the only example that I'll show the actual math for. For angular acceleration, I took final angular velocity of 0.57 radians per second. I subtracted the initial, which would be 0, and divided that by 0.3 or 3/10 of a second, which ended us with 1.9 radians per second squared. I take my angular acceleration and multiply it times the radius, which is 0.43 meters or 43 centimeters, and I get 0.82 meters per second squared. All right, and that is the tangential acceleration. Then we go to the calculations for the hips. Angular displacement of 1.22 radians, arc length of 63.44 centimeters, angular velocity of 4.07 radians per second, and then an angular acceleration of 13.57 radians per second squared. That translates to a tangential acceleration of 7.06 meters per second squared. And then finally, the shoulders, angular displacement 0.96 radians, angular velocity 3.2 radians per second, angular acceleration 10.67 radians per second squared, which translates to a tangential acceleration of 6.4 meters per second squared. So how does this look for translation to the bar? The bar's displacement during that 3/10 of a second was 0.608 meters, with a velocity of 2.03 meters per second and an acceleration of 6.77 meters per second squared. I take my mass, which is my body mass minus my leg mass, which is 83.77 kilograms. I multiply that times my tangential acceleration at the hips, which is 7.06 meters per second squared, and I come up with 591.42 newtons of force on the hips. Force on the bar would be the weight of the bar, which is, it's a 45-pound bar, so 20.45 kilogram bar, times 6.77 meters per second squared, which is our bar acceleration, and we get 138.45 newtons of force on the bar. As we move to position B, which is the following tenth of a second, I get zero change in the knee angle, so I remain at 65 degrees. The hip, however, has an angular displacement of 0.44 radians, a velocity, angular velocity of 4.4 radians per second, an angular acceleration of 3.3 radians per second squared, and a tangential acceleration of 1.72 meters per second squared, which ends up being significantly less than position A. Also, at the shoulder, I get angular displacement of 0.7 radians, angular velocity of 7 radians per second, an angular acceleration of 38 radians per second squared, and a tangential acceleration of 22.8 meters per second squared. This translates into a bar displacement of 0.304 meters during that 1/10 of a second, which gives me a velocity of 3.04 meters per second and an acceleration of 10.1 meters per second squared. This translates also as a 144.08 newtons of force on the hips, compared to the 591 roughly newtons of force on position A, but 206.55 newtons of force versus the 138 roughly newtons of force at position A. As we move to the finished position, the final position, which is position C, takes between 0.4 seconds to 0.8 seconds to move from position B to position C. At the knee, I have a 0.44 radians of angular displacement, angular velocity of 1.1 radians per second, an acceleration of 2.75 radians per second squared, which gives me a tangential acceleration of 1.18 meters per second squared. The interesting part, and the part that translated as useful information to me, was here at the hips. At the hips, I had a angular displacement of 0.96 radians, angular velocity of 2.4 radians per second, angular acceleration of negative 8.6 radians per second squared, which translates to a tangential acceleration of negative 4.47 meters per second squared. So I significantly slowed down in the last half of the movement. Slowing hip speed on a hip centric movement is very inefficient, or it lacks efficiency. And then at the shoulder, angular displacement of 0.87 radians, an angular velocity of 2.17 radians per second, and an angular acceleration of negative 12.08 radians per second squared. And this translates to a tangential acceleration of negative 7.25 meters per second squared. How this looks on the bar gives me a bar displacement during the 0.4 of a second of 0.912 meters, which gives me a velocity of 2.28 meters per second and an acceleration of negative 1.9 meters per second squared. So a significant decrease in bar acceleration due to the lack of hip acceleration. This translated as a negative 374, roughly 375 newtons of force on the hips and a negative 39 roughly newtons of force on the bar. So doing this biomechanical analysis on the thruster, going from start position to position A, position B, and to position C, what I found out was that I have a great amount of power and acceleration going from position A to position B, but going from position B to the second half of the movement, or the next 4/10 of the second of the movement, I significantly lose hip acceleration and bar acceleration. This has been a biomechanical analysis of the thruster.